In question 1, we've got a car initially at rest, accelerating along the road with a constant acceleration of 3.2 meters per square second, and we need to find the speed of the car after 5 seconds. So let's start by writing down the information. We've got the car initially at rest, so u is 0. We've got an acceleration of 3.2, and we know that the time is 5 seconds. So I'll be using v equals u plus at, the Suvad equations. So it's gonna be 0 plus 3.2 times 5, which gives an answer of 16 meters per second for the speed. In part B, we need to find the distance traveled in the first 5 seconds. So this time I will be using s is ut plus a half at squared. So in our case, u is 0, and we've got a half times the 3.2 times the 5 squared, and this gives an answer of 40 meters. In question 2, we've got the particle P of mass 5 kilograms being pulled along a rough horizontal plane by a horizontal force of 28 newtons, with the only resistive force being the F newtons shown here. We need to find the magnitude of the normal reaction of the plane on P, and I will start by adding the forces missing from the diagram here. We've got the weight, which is 5g, and we've got the reaction there, and we know that the vertical forces should be balancing out, and therefore R is equal to 5g, which gives an answer of 49 newtons. We are then told that the particle is accelerating along the plane at 1.4 meters per square second, and we need to find the value of F. So let me add the acceleration pointing to the right, and therefore we have a net resultant force to the right. So I'll be doing forces to the right, 28 minus forces to the left, which is F, is equal to mass times acceleration. This leads to 28 minus F being equal to 7, and therefore we get that F is 21 newtons. And finally, in part C, we've got the coefficient of friction between P and the plane being nu, and we need to find the value of nu, giving our answer to two significant figures. Now, since we've got motion, since the particle P is moving to the right, this means that the F, the resistive force, the frictional force, has attained its maximum value, and this is given by F being equal to mu R. We have already established that F is 21 and R is 49, so 21 is 49 mu. I will divide by 49, but I need to be giving my answer to two significant figures, and therefore we arrive at 0.43 to be the value of mu. In question 3, we've got the velocity vector of a particle P given here in terms of I and j, and we need to find the speed of P at time t0. So obviously the first thing to do is start with substituting t0. So if we put t is 0, we get that the velocity vector is equal to 7I minus 3j. Well, we're being asked to find the speed, and speed is the magnitude of velocity. So to find the speed, I will simply use Pythagoras. It's 7 squared plus negative 3 squared and all square root, which gives an answer of root 58, and it's meters per second. In part B, we need to find the value of t when P is moving parallel to I plus j, and we know that the idea of motion is stemming out of the velocity vector. So let me write out the velocity vector in column form. We've got t squared minus 3t plus 7 and 2t squared minus 3, and we know this is moving in the direction of I plus j, so this is parallel to 1, 1. Which means that the ratio of the I and the j is equal to 1 over 1. So t squared minus 3t plus 7 over 2t squared minus 3 is equal to 1. I will cross multiply to get t squared minus 3t plus 7 is equal to 2t squared minus 3. And I will be collecting everything on the right hand side to get 0 is t squared plus 3t minus 10, which factorizes into t plus 5 and t minus 2. And therefore we either have t plus 5 is equal to 0 or t minus 2 is equal to 0. Well, if t plus 5 is 0, this means that t is negative 5, which is of course rejected. It's not valid because we've got t being time, and therefore it can only attain positive values, and we conclude that t is equal to 2. In part C, we need to find the acceleration of P at time t seconds, and we know that the acceleration vector is simply the derivative of the velocity vector with respect to time. So if we differentiate the I component, we get 2t minus 3 so 2t minus 3i, and if we differentiate the j component, we get 4t, so plus 4tj, and this is meters per square second. And in part D, we're being asked to find the value of t when the direction of the acceleration of p is perpendicular to I. So the I vector is that vector that takes me to the right. So if I'm perpendicular to I, it could be that I'm going up, so in the direction of j, or down in the direction of negative j. Well, we have already established that the acceleration vector is 2t minus 3, the I component, and 4t, the j component. Again, I'm writing this in column form, and this should be parallel to 0 plus minus 1. So I'm accounting for the fact that I could be going up or down, but surely the I component is 0, and therefore I can simply set 2t minus 3 to be equal to 0, which leads to 2t being equal to 3, and therefore t is equal to 3 over 2. In question 4, particle P is moving on a smooth horizontal plane. We've got the constant acceleration with which the particle is moving. We know that at time t0 we're passing through A, and 5 seconds later we're passing through B. We've got the velocity of P at A being negative 16I minus 3j meters per second, and we need to find the speed of P as it passes through B. So I will start by stating that V is equal to U plus AT, and obviously we are in vector mode here. So in our case, the velocity at B will be given by the initial velocity, which is minus 16I minus 3j, plus the acceleration, which is 2.4I plus j times the time, which is 5. So this means I've got minus 16I minus 3j, and then we've got plus the 12I plus 5j. So this leads to minus 4I plus 2j. Well, we've been asked to find the speed, so I need to take the magnitude of this velocity vector. So the speed will simply be the negative 4 squared plus the 2 squared and all square root, which gives an answer of 2 root 5 meters per second. We then have that the position vector of A is 44I minus 10j, and at time t being capital T seconds, where capital T is greater than 5, we pass through the point C with position vector 4I plus cj, and we need to determine the value of capital T. Well, let me start by writing that the position vector at any point is given by the initial position vector, so the position vector at A plus ut plus a half times the acceleration vector times t squared. So the position vector at C is 4I plus cj, and this should be equal to the position vector at A, which is 44I minus 10j, plus the initial velocity times t, so the minus 16I minus 3j times the capital T, plus a half times the acceleration vector, which is 2.4I plus j times t squared. Well, if I look at the I components, the 4 should be equal to the 44 minus 16t plus a half times 2.4 times t squared. So we arrive at 4 being equal to 44 minus 16t plus 1.2t squared. So we're looking at a quadratic in t. So if I collect everything on the right hand side, I get 0 is 1.2t squared minus 16t plus 4t, and I can use the quadratic formula to determine the values for t. So we've got capital T being minus the negative 16 plus minus the negative 16 squared minus 4 times 1.2 times 4t square root, and all of it divided by 2 times the 1.2. So this gives an answer for t of 10, or alternatively for t being equal to 10 over 3. Now we have been told that capital T is greater than 5, which means I need to reject the value of 10 over 3 since t is greater than 5, and therefore we conclude that capital T is equal to 10. In part C, we need to find the value of C, and obviously if we recall the expression we obtained, I will now equate the j components, and we've got that C is equal to negative 10 minus 3 times capital T plus a half times the capital T squared. Well, we have found the capital T to be 10, so minus 10 is negative 3 times 10 plus a half times the 10 squared. And if we plug this on the calculator, we arrive at C being equal to 10. In question 5, we've got a small ball projected with a speed of 28 meters per second and an angle alpha above horizontal ground, and we know that it passes through the point A capital T seconds later. The point A is found 40 meters to the right and 20 meters above ground, and we need to show that capital T is 10 over 7 cos alpha. Well, I will start by resolving the velocity into the horizontal and vertical components, and the horizontal component is 28 cos alpha and pointing to the right, whereas the vertical component is pointing upwards and it's 28 sine alpha. So looking at the horizontal dimension of the problem, we've got that the velocity, initial velocity is 28 cos alpha. The displacement along the horizontal is 40, and the acceleration is obviously 0. So I'll be using S is ut plus a half at squared, which leads to 40, the horizontal displacement being 28 cos alpha times the capital T plus 0, because the acceleration along the horizontal is always 0, where the 40 with the 28 simplified to give me a 10 and a 7, which means that 10 over 7 cos alpha is equal to T as required. In part B, we need to show that tan squared alpha minus 4 tan alpha plus 3 is equal to 0, and I will now consider the vertical dimension of the problem. So the initial velocity, the vertical component of it is 28 sine alpha. The vertical displacement Sy is equal to 20, and the vertical acceleration is negative g, which is minus 9.8. I will again be using S is ut plus a half at squared. So I've got 20 is equal to 28 sine alpha times capital T plus a half times the minus 9.8 times the capital T squared. And I will be substituting capital T with the expression we obtained from part A. So 20 is 28 sine alpha times 10 over the 7 cos alpha minus the 4.9 times 10 over 7 cos alpha squared. This takes me to 20 is equal to 40 tan alpha minus 10 sec squared alpha. I will divide throughout by 10, so the zeros will cancel out, and I'll be using the identity that says that sec squared is 1 plus tan squared. So I've got 2 is equal to 4 tan alpha minus 1 plus tan squared alpha. I will expand to get 2 is 4 tan alpha minus 1 minus tan squared alpha, and I will collect everything on the left hand side, leading to tan squared alpha minus 4 tan alpha plus 3 is equal to 0 as required. In part C, we need to find the greatest possible height in meters of the ball above ground as we move from O to A. So I will start by taking the quadratic in tan alpha and factorizing. This gives me tan alpha minus 1 times tan alpha minus 3 is equal to 0, which means that tan alpha minus 1 is equal to 0, or tan alpha minus 3 is equal to 0, and therefore we've got tan of alpha is equal to 1, or tan of alpha is equal to 3. Now to find the maximum height at 10, I'll be using v squared is u squared plus 2as, and we know that if we consider the vertical component of the velocity, when we attain a maximum height, this will be 0, and therefore we get 0 squared is 28 sine of alpha squared plus 2 times the acceleration, which was negative 9.8 times the height, and we're trying to find this height. This leads to 0 is equal to 784 sine squared alpha minus 19.6 h, and therefore 19.6 h is 784 sine squared alpha, and if I divide both sides by 19.6, I get h to be 40 sine squared alpha. Now we know that tan alpha is 1 or tan alpha is 3, so I could actually draw two triangles, and we've got if tan alpha is 1, this will be 1 over 1, which means the hypotenuse is 1 squared plus 1 squared square root which gives an answer of root 2. Whereas if tan alpha is 3, then the opposite is 3 and the adjacent is 1. So the hypotenuse is 3 squared plus 1 squared, which is equal to root 10. This means I can derive the sine alpha here to be 1 over root 2, which numerically is 0.707 dot dot dot. Whereas in the second case, we get sine of alpha is equal to 3 over root 10. If you put this on the calculator, you get 0.948 dot dot dot. Remember, we're trying to determine the maximum height attained, so I'm gonna pick the maximum sine alpha, which is the 0.948, or exactly the 3 over root 10, and therefore we conclude that the maximum height attained, h max, will be equal to 40 times the 3 over the root 10 squared, which gives an answer of 36 meters. Indeed, we need to state another limitation of the model apart from not including air resistance. Well, if we read the question carefully, we see that the ball is modeled as a particle. This means that the dimensions of the ball are not taken into consideration, and this is a limitation of the model. Alternatively, someone could have mentioned that the value of g we have used is not accurate, and this is also considered to be a limitation of this model. In question 6, we've got the rod AB of mass capital M and length 2a. Now we've got the end A on rough horizontal ground and the end B against a smooth vertical wall. The rod is making an angle theta with the ground as shown, and it's resting in limiting equilibrium. We need to state the direction either to the left or right of the frictional force acting on the rod at A, and we need to give a reason for our answer. Well, before I answer this first part, I will start by adding all the forces acting here. So we certainly have got the weight, capital mg. We've got the reaction at A pointing upwards, which I will call capital R, and we've got the reaction at B pointing to the left, and we call this capital S. Now, for this to be in limiting equilibrium, we know that there is a frictional force acting at A, and we need to counterbalance the S, which is pointing to the left, which means that the resistive force, the frictional force at A, should be pointing to the right, and I'll call this F, and therefore we conclude in part A that the frictional force at A is acting to the right, since the only other horizontal force is the reaction at B, which is acting to the left. In part B, we are modeling the rod as being uniform, and we need to take moments about A to show that capital S, the reaction at B, is given by a half capital mg cot theta. So going back to the diagram, I will add the distances. So if I take moments about A, this means that the R and the F have no moment about A, and therefore the clockwise moment is due to capital mg, which is acting at a distance of A cos theta, whereas for the anti-clockwise moment due to S, this one here, the distance at which it's acting is this one, which is given by 2a sine theta, and therefore we can proceed. We say we take moments about A, and we've got A cos theta times capital mg, the clockwise moment, is equal to 2a sine theta times the S. Well, I will start by simplifying the A with the A, and then I will divide both sides by cos theta. So dividing cos theta, the left hand side will simplify out, whereas on the right hand side I get tan theta. So this leads to capital mg is equal to 2 tan theta S. And if I divide both sides by 2 tan theta, I get a half capital mg cot theta, because 1 over tan is cot, is equal to capital S as required. We are then told that the coefficient of friction between the rod and the ground is mu, and tan theta is 3 over 4, and we need to determine the value of mu. Well, starting with tan theta is 3 over 4, this means that cot theta is simply the reciprocal of this, so it's 4 over 3, and this means that the reaction at B, the capital S, is a half times the mg times the cot theta, which is 4 over 3, and this gives an answer of 2 mg over 3. And I can therefore proceed by considering the horizontal and the vertical forces. Since we're in limiting equilibrium, these need to balance out. So the horizontal forces, looking at the diagram, means that capital F is equal to capital S, whereas the vertical forces means that capital R is equal to capital mg. So we can equate this. So setting F to be equal to capital S, we have already established that capital S is 2 mg over 3, whereas for the vertical forces we've got capital R is equal to mg. Now, us being in limiting equilibrium simply means that capital F is equal to mu R, and therefore we've got that 2 capital mg over 3 is equal to mu times mg. Now we can see that the mg will cancel out, and therefore we conclude that the mu is equal to 2 over 3. In part D, we need to find in terms of capital M and G the magnitude of the resultant force acting on the rod at A. So if we recall the diagram, at A we've got the reaction force and the frictional force. We have already established that the reaction force is equal to capital Mg and the frictional force is 2 mg over 3. And to find the magnitude of the resultant force, I will simply be using Pythagoras. So it's going to be mg all squared plus 2 mg over 3 all squared and square root. This gives me m squared g squared plus 4m squared g squared over 9 and all square root, which gives an answer of 13m squared g squared over 9 and all square root, which simplifies to capital mg root 13 over 3 newtons. Now, in a new model, the rod is modeled as being non-uniform with its center of mass closer to B than it is to A. Now we are calculating a new value for the reaction at BS, and we still have that tan theta is 3 over 4, and we need to state whether this new value for S will be larger, smaller, or equal to the value obtained under the initial model, fully justifying our answer. We're looking at the diagram once more. These are the forces acting. We are moving the center of mass closer to B, so somewhere there. So if we take moments about A once more, we can see that the clockwise moment due to the weight is going to increase because the distance at which it's acting is now greater than the original model, the initial model. So we can simply say that taking moments about A, we see that the clockwise moment of the weight is now greater, and therefore this means that the new value of S will need to increase and will therefore be larger.